When a sound is created, the sound wave propagates in all directions. If more than one sound run into each other, they interact with each other by a principle called superposition. In superposition, the two sound waves meeting gives a resulting sound that's a combination of the pressures from those two sounds added together. So for example, in a waveform graph, you would add the pressure at each point in time or space where the two sounds are interacting to get the combined pressure. This is kind of tedious to do, but it gets the idea across. It's also the case that the two sounds in a way don't affect each other. They can cross each other or pass through each other, and if they move away from each other, they go back to being the very same sound that they were. There's an example in this link for a YouTube video where you can see a kind of a moving waveform demonstration of what superposition would look like in terms of pressure measurements. When two waves come together, we have some terminology for how they interact with each other as different types of interference. There is destructive interference when interference results in a decreased overall amplitude. There is constructive interference when the interference results in an increased amplitude. There would be no interference if one or both of the waves happen to be at zero relative to atmospheric pressure. So here we have two waves. They happen to be at roughly the same frequency, but they aren't aligned with one another in terms of phase. The very first arrow on the left here, we have one that's at a negative pressure and the other at a positive pressure. So if they were to overlap at that point in time, that would be a case of destructive interference. They would partially cancel each other out. This second arrow here would be a case of constructive interference. The first wave is at a negative pressure below atmospheric pressure. The second wave is also at a negative pressure below atmospheric pressure. So when the two come together, the combination would be an even greater negative pressure. The third arrow here, the wave on the top is at a positive pressure. The wave on the bottom is at a positive pressure. And so the combination of those two waves at that point in time would be an example of constructive interference. On the fourth arrow, we have the wave on the top at a negative pressure, the wave on the bottom at a positive pressure. So when they come together, they will partially cancel each other out. That would be an example, again, of destructive interference. We have no interference in cases where one wave is at zero. So for example, at the top, it starts at zero. The next zero is here at roughly 0.0025. The next zero looks like it's right at 0.05. So all three of those points would be cases of no interference. For the bottom wave, we have a zero at, I don't know what, maybe 0.002. So there would be no interference there. Another spot at maybe 0.004, there would be no interference there. Another spot at maybe 0.006, there would be no interference there. Any place where the wave is at zero atmospheric pressure. Some additional terminology for the propagation of a sound, for a sound radiating away from a source. We can have the incident wave, that is the sound wave that's generated by a source, and it's generally things vibrating that create sound waves that displace air molecules. Absorption is a case where the sound is reduced in amplitude due to interaction with an object. That relates to the object's elasticity, for example, if it's a soft surface. This can also happen in cases where a sound wave gets trapped within a particular space, which is relevant in the case of the vocal tract, for example. There is also reflection of a sound. If a sound isn't transmitted or absorbed, part of the sound bounces off of a surface at its boundary. and it travels in the opposite direction from the incident wave generating the sound. Or maybe the opposite direction isn't the best term in this case, because we have special terms for different types of refraction. In the case of diffraction, there's a change in direction of the sound wave as it goes through an opening or it travels around an obstacle. So this happens, for example, when speech sounds hit the opening of the mouth at the lips, and the sound then radiates in all directions. We also have refraction, a change in direction as the wave hits a medium that has a different speed of sound. So for example, as sound propagates from the air into a wall, and it does sort of vibrate the molecules that make up the wall, but the speed of sound will be different in that wall. And so if the sound hits it at an angle, the difference in speed of sound is going to cause a change in direction of that sound as it propagates through the wall. Wave reflection is going to be an important concept when we talk about how sound waves bounce around inside the vocal tract. I have links to a couple of visualizations here that use a rope. In this first visualization, we have a rope that has different types of reflections depending on whether the far end of the rope is fixed or not. So if you go and watch the video, you will see that the wave that's created in the rope by the person holding the rope acts differently depending on whether the far end of the rope is in a fixed position or whether it's connected to another piece of rope such that it can move around and it's not in a fixed position. This will also be relevant to how sound waves propagate around in the vocal tract. There is a special property of reflection. If a wave has just the right frequency, its reflection will help enhance it. So in the superposition, we always have constructive interference, you might say. When that happens, we get a thing called a standing wave, a stable wave that has specific points in it that reflect its stable state. So the second link there takes you to a video by the same person with a rope showing examples of different standing waves in that rope. When we get a wave interacting with itself, so going and reflecting off of a surface, for example, we can get resonance, which is the enhancement of a wave by basically making it a standing wave. This link on this slide is an example of different levels of resonance. It's a little bit longer of a video where the person has a device that allows them to precisely control the frequency of vibration of the string, basically. So they can show different resonances for the vibration of the string. That will be relevant to the contents of the video about resonances in the vocal tract. Here is a graphical picture of what resonances look like. These drawings look like the standing waves in the string that you can see, but these graphs also are an accurate representation of resonances for a sound wave if you interpret the vertical axis as pressure variation in the standing wave. We have three different resonances here, labeled 1, 2, and 3, and for each one we have something that looks kind of like a waveform graph with a solid part and a dotted part. And the idea of those two lines is to kind of show you the range of variation that you get in the standing wave. When you have a standing wave, there are special points referred to as nodes where the pressure is always 0. and antinodes, where the pressure always varies from a maximum positive value to a maximum negative value. So I've indicated a couple of those node and antinode points in these graphs. There are more nodes and antinodes. Any place where there is a 0, like over here on the left for the first wave, the second wave, and the third wave, or in the middle of the second wave, 2 different places in the middle of the third wave, we have places where the pressure is always 0. Antinodes have maximum variation. In the first wave, there is 1 antinode right in the middle. In the second wave, in addition to the antinode I've marked, there is a second one that basically between the nodes and antinodes divides the waves into quarters. And in the third wave, we have additional antinodes, and the nodes and antinodes end up dividing the wave into sixths, basically. So we get resonance when we have a sound wave, for example, vibrating in a space where the response of the space to the incident sound wave has a frequency that matches or comes close to its own natural resonance frequency. Given that idea of a natural resonance frequency, then, we can separate out a free resonance, the natural vibrating frequency of an object. In the demonstration, the swinging of the rope is done at different frequencies until a stable pattern emerges, versus a forced reference. Forced resonance, pardon me. Forced resonance is a vibrating frequency that's applied to an object. So in the demonstration, or the 2 different videos, one was a hand swinging the rope, the other was a machine causing a speaker to vibrate that was causing the rope to move. The frequency of that movement of the hand or vibration of the stereo surface, or the speaker surface, I guess I should say, is a forced resonance. So depending on that frequency, that might line up with the natural free resonances of the object, or it might not. If it does line up well, that's where we get standing waves, that's where we get an enhancement of the amplitude of a wave, and I've used expressions like a wave fits well in a space to represent that idea. So if we then apply this to speech and acoustics, we have an acoustic resonance when an air-filled container or cavity is forced to vibrate by an applied frequency, a frequency created by a sound wave propagating into that air-filled container. We apply that specifically to the vocal tract, and we have vocal tract resonances, the natural vibrating frequencies of the vocal tract, which changes given its shape. We can approximate what vocal tract resonances might look like by looking at the resonance of simple tubes. So the resonant frequency of a tube is related to the length of the tube and the shape of the tube, and whether that tube has closed or opened ends. And we can approximate various vocal tract configurations by considering them to be like a tube that has closures or constrictions in it that create spaces of different lengths.